right, so here we have two limit problems that we're going to look at, and these are a little bit more difficult limits than some of the ones that we had looked at before. Obviously, on both of these, you cannot just use a substitution shortcut and substitute in x equals 0 on either of these. For both of these functions, that would make the denominator 0, which doesn't necessarily mean that the limit doesn't exist. It just means you can't use a substitution shortcut to evaluate it. And these both involve a lot of trig functions, so we might think a little bit about the special limits that we've already looked at. So we started with one special limit. I'm just going to write those both up here. The limit as theta approaches 0 of sine theta over theta, and that limit is 1. And then we used that special limit to derive another special limit that involves cosine. We did that one with x's. I'll write that one with x here. Limit as x approaches 0 of cosine of x minus 1 all over x. That limit is 0. So we're going to reference both of those special limits when we do these other limit problems. And so we won't use both of those in both problems, but we'll use both of them in these two problems. All right, so we're going to start by thinking about these trig functions that we have and thinking about how we can relate them to the trig functions here in these special limits. All right, so on this first one, I noticed that I have a cosecant function and a tangent function. I would probably try to rewrite all of those in terms of sines and cosines. And so I notice sometimes students have a lot of trouble remembering cosecant and how that's related to sines and cosines. If you're having trouble with that, make sure you remember those things. You're going to need them several times throughout this semester. All right, so you want to remember cosecant is 1 over sine. And then most students remember tangent is sine over cosine. So the first thing I'm going to do on this first problem here is rewrite all of that in terms of sines and cosines. Also, when I do that, notice that tangent is sine over cosine, so it has a fraction on the denominator of a fraction. So in order to clean that up a little bit, we'll multiply by the reciprocal on that one. So for this problem, when I rewrite everything in terms of sines and cosines, this numerator here, I would probably rewrite that as x squared over sine of 4x. X squared over sine of 4x because cosecant is 1 over sine. All right, so that's just the numerator. And then I could have all of that over sine of 5x over cosine of 5x, but instead of putting a fraction over another fraction, we're going to multiply by that reciprocal. So the reciprocal of sine over cosine would be cosine of 5x over sine of 5x. OK, so all I've done is rewrite the original expression in terms of sines and cosines. And then we might notice that we have some things here also related to our special limit form that we have right here. So I have an x over a sine of 4x. And then I also have this other sine of 5x on the denominator. I'm going to split this x squared up into an x and another x. So I can have one of them with the sine of 4x and one of them with the sine of 5x. So we've looked at some other problems like this that were a little less complicated, but this is the kind that a lot of students have trouble with. So slightly more difficult example here. All right, but I'm just going to use the same concept as before, just do a little bit of regrouping here. So I'll have x over sine of 4x. And then for the other x will be over the sine of 5x. I'm just using properties about multiplying fractions here to regroup this. And then I also have this cosine 5x factor, which I'll just pull out here separately. All right, so I've regrouped it a little bit. We're getting closer to this special limit form that we've looked at before. There are two things that I wish were true about both of these first ones. One is I wish I had some extra constants, so we know how to deal with that. The other thing to notice is that these are upside down. These fractions are upside down from the way I wish they were for that special limit form. So we're going to deal with both of those issues here. We deal with the constants first. I would like to multiply this by 4 on the numerator so that the argument of the trig function matches this other part of the fraction there. So these match, 4x and 4x. I can't go around just putting a 4 in, though. I have to balance that. So I'm going to do that out here to the side and divide by 4 to balance that. So I've multiplied by 4 and divided by 4. And then similarly here, I will multiply by 5, and then I will need to divide by 5. So I'm dividing by 20 over here. All right, so I now have these matching. So I've adjusted those constants to make those things match. The other thing that I will do is use another property of algebra that at first will make this expression look much more complicated than it really is, but will get us the expression so that we have this fraction right side up, sine theta over theta, instead of the reciprocal of that here. All right, so I'm just going to use some more properties of algebra here. All right, so this is going to look more complicated here, but when I want to flip a fraction upside down, what I really want is the reciprocal of that. So algebraically, we could write that as 1 over. So I'm writing 1 over the reciprocal of this, sine 4x over 4x. And so that expression that I have now on the denominator there is my sine theta over theta form, so that that matches exactly that form there. I'm going to do the same thing here. So I'll have 1 over sine 5x over 5x. And then this one, I don't need to re-manipulate that, so I'll just write that as cosine 5x all over 20. OK, so at this point now we're ready to evaluate this limit using the special limit form. We're really just using this first one in this problem here. And also some theorems about combining limits. So we have theorems about combining limit functions. So provided this limit of this denominator exists, we have a theorem about division of limits. So we would have 1 over whatever this limit is. All right, so using that special limit and a theorem about combining functions, we get that that's 1 over 1 or 1. This one is also similarly 1 over 1. There's that special limit. And then here, at the end here, this cosine function is well behaved. 0 is in the domain of cosine 5x. So we can just use a substitution shortcut to finish this part here. So we'll have cosine of 0, 5 times 0 is 0, all over 20. All right, and then I just need to finish and evaluate that. Cosine of 0 is 1. So I have 1 times 1/20th. So we get 1/20th, or 0.5 for that limit. OK, so slightly more complicated problem. You've probably looked at several simpler examples like that, but I just wanted to do a slightly more complicated one. A lot of times students have trouble with one like that. All right, so for this next one, kind of similarly, we're just going to refer to these special limits. This is the first one I've really done where we've had to use this second special limit that we derived. And it may not be obvious right at the beginning how this second one comes up. You don't see any cosine functions here at all. One temptation might be to try to split things up here and get a sine theta over theta, but algebraically, you're not going to be able to split up this x squared into two separate denominators with this subtraction here. Notice that I split up an x squared here, but I had multiplication in the original problem. So you're not going to be able to use this exact same strategy on this other one. And this is a harder problem, and I would say without a hint, most students probably would have a hard time figuring out where to go with this problem. But the hint is trig identity. So whether you remember those or not, once I write it down, you should be able to actually use the trig identity to finish the problem here. So there's a double angle identity for sine. That is one that I find that a lot of students do remember. So maybe you remember that one. If so, awesome. If not, once I remind you of it, then you should be able to finish the problem. All right, so sine 2x, that identity is that is 2 times sine of x times cosine of x. And then I have this other part here. And then I have an x squared on the denominator. All right, I might notice that I have a common factor. I have two terms on the numerator. There's a common factor of 2 sine of x. So I'm going to factor that out. And then I'm left with cosine of x minus 1. All right, and at this point, I do have multiplication. So now I can split that x squared up in terms of multiplication. And you'll see that we have these two special limit forms right here. So I'm going to put the 2 separately out front here. And then I'll have sine of x. So I have 2 times sine of x over one of these x's. The reason I'm grouping it this way is so that I can get it into the form of these special limits here. And then I'll have another fraction here that is times cosine of x minus 1 all over the other x from the x squared. Okay, so all I've done is use some algebra there, trig identity, and then a little bit of algebra to rearrange that so that I get these special limit forms here that we've worked with before. All right, and so at this point now we're ready to use those special limits and finish this problem here. So 2 is just 2, constant. The sine of x over x as x approaches 0, that's one of those special limits. That one's 1. And this is the new one that we just worked on, and we showed that that limit is 0. So 2 times 1 times 0, our overall answer for this problem then is going to be 0. All right, so if you can handle ones like this where you have to use a lot of manipulation and trig identities, then you can probably handle any of these special limit problems. These are a little bit more difficult, and so they do take some practice. If you struggle with ones like this a little bit, that's okay. Just keep at it. Keep thinking about those trig identities, if those might help. These definitions about cosecant and tangent, rewriting everything in terms of sines and cosines, and ultimately remembering that your goal is to use these special limits that we've worked on.